right. So equilibrium vapor pressure. I like to draw this sort of thing. So if you're familiar with a terrarium, I don't know, like a terrarium where you have the dirt and you grow a little cute little plant, and you obviously, in order for that plant to grow, you have to give it some water. So because plants need sunlight, soil, and water. Although that's even questionable. I don't know. I'm not a plant person. But if you think of a terrarium, and this, I draw a lot of these. So this lecture kind of goes like this. This is my water down here. I have a watch glass over my beaker to make it a closed system. I know it's not a closed system, but I'm pretending it is. If I were to come back later, given amount of time, it could be kind of like a terrarium. I could have like water condensed like that. I'm going to put an L down here standing for liquid. And one of the cool things about liquid, and this, when I first started thinking about this part, it's weird to think that liquid can transition from liquid to a gas without boiling. It doesn't have to boil. Okay, because what it will do is some of those liquid water particles will break their intermolecular bonds. They will go up into their gaseous state. I'll put a G up here. And then some of those gases will condense down to form liquid again. Okay, that's why, of course, we call, as it's going from liquid to gas, we call evaporation. As it's going from gas to liquid, we call that condensation. That's what you're getting when you get a kind of condensation on the wall. But if I let the length of my arrow be an indication of how much it's doing, the rate at which it's doing it, that at equilibrium, we say the rate of evaporation is equal to, the rate of evaporation is equal to the rate of condensation. That's equilibrium. So, when we're talking about, in this case, the equilibrium vapor pressure, I could isolate those cute little H2O gas particles, and I could look at the pressure that it has, and that's my equilibrium vapor pressure. So I'll put P sub H2O gas. That is my EVP, equilibrium vapor pressure. I like the word equilibrium vapor pressure. It sounds more descriptive, but for whatever reason, actually, sometimes you're going to see me or see us in the scientific community talk about equilibrium pressure just in terms of vapor pressure. It is the equilibrium vapor pressure. I'm not so sure about that. Okay, so that's kind of what we have. So I've got three scenarios to kind of show you. I think we looked at, this is a manometer, I want to say. So this is mercury right here, this gray, and this actually is, you can see the liquid and the kind of, you see the evaporation from the liquid to form little gas particles. Check out, keep an eye on this gas gauge right here. This, not gas gauge, this pressure, well, gas pressure gauge right there. So remember how these work. I think we've talked about these. This is my HG liquid mercury. I think we've talked about these before. As the pressure of this gas increases, it forces more mercury down. That liquid mercury will go down, like this. If you compare the two, you don't go down much at all. Straight edge here. They look pretty similar. Looks like it went up, actually. But what it's supposed to do, and I just think they did it bad here, this, I think, should have gone down, and this would have gone up. But what happened to the pressure meter, pressure gauge? It went up. Let's see. I have to tell Carl, I just think that they did that one too. Maybe they did all of these wrong. Maybe this was the final one, and then actually this one should have been equal. Yeah, I just think that they screwed these up. These two are wrong, and I think this one's right. I think this should have been up here equal. Okay, because I say that because here, finally, of course, we have the most deflection, the most particles in their gaseous phase, makes sense, the highest gas pressure. And then actually, as you see this difference right here would be an effect from this gas pressure. Wow. I just think they screwed up. But anyway, this part was One of the things I don't like about this figure also is, you know, when I drew my beaker a minute ago, I mean, they've only got evaporation. To me, we definitely have condensation going on too, until an equilibrium is reached, but they don't show both the arrows going both ways. But they do show the particles increasing, the gas particles increasing. So, I don't know. It's a free textbook too. What do you expect? I'm sorry. No, I think it's a good book. So this is a figure from a different textbook, and it does more of what I expect. So this is just a bell jar to create an isolated system, much better than my wash flat over beaker. So here's your pan of water. If this is a dry atmosphere, one of the things we know, or one of the things you might expect, is you only have evaporation. After a while, you get these are liquid water, not liquid, sorry, these are gas water particles. Okay, after a while, you have the blue are the condensation. So you have the condensation. Now, what's doing more here? Is evaporation more or condensation more here? Evaporation more, because you can see, you can count the cute little red ones. Okay, what about this one? What's more? Condensation. Let's see, red ones. 1, 2, 3, 4, 5, 6. Blue ones. 1, 2, 3, 4, 5. Up, 6 and 6. They're equal. It's at equilibrium.
Who's counting the gray ones? Sorry.
There's lots of gray ones. And of course, at equilibrium, we've maxed out. And in meteorology or weather, we talk about the air is saturated. We've maxed out with the vapor of that type that can be at that temperature. That's pretty exciting. Yep. So C is equilibrium. Now, I'm pretty sure this one's right. This has liquid mercury, the silver or the gray is the liquid mercury. And I'm pretty sure in Unit 5 in Chem 1, we talked about gases, and we talked about the mercury barometer. So this is kind of the way a mercury barometer works. Basically, you have an open pan of liquid mercury, you have the pressure, okay, on it, and what you've done is taken a tube that's closed at one end. Okay, you pull the vacuum on it, put your finger on one end, set it in the pan of mercury, and then that mercury will rise relative to the amount of pressure, atmospheric pressure that's on the open pan. So that's what we call the barometric pressure, or the environmental pressure, atmospheric pressure, PSVAR. Well, we've been talking about, and I'm going to use the word volatile, and I'm going to define volatile here in a minute, but volatile liquid is something that can, without boiling, go into its gaseous phase. Oh my gosh, if you have rubbing alcohol, I mean that stuff can, and that's why it makes you cold, because as it evaporates, you get cold. It can definitely go from a liquid to a gas without boiling. So we have some sort of volatile liquid in this syringe, and it must be less dense, so it's going to float on top of our mercury. It's kind of a clever way to admit it. So given a little bit of time, that volatile liquid is going to go ahead and create pressure inside of that area. Okay. So actually, we're seeing that right here even. Check out the height of the mercury that went up in the tube. This is barometric pressure. This is just from the pressure of the atmosphere, okay? But notice the depressed here, it only went up this high, okay? And the reason it only went up this high is because these extra gas particles in there. So we can actually get a fix on the pressure of that gas. The difference between these two is this one's thinner and this one's wider. Remember, the cool thing about how mercury barometers work is it doesn't matter the diameter of the tubing. I'm just kind of showing that with the same amount of deflection. Even thinner, same height. Okay, this one, I am going to heat up my system. I'm going to heat up the liquid. What should happen to the gas particles if I heat them up with regard to pressure? It will increase. Yep. So that's why this one looks as it does. So the pressure of the gas inside increases. And these actually just kind of talk me through it. That's without any volatile substance. That's with volatile substance. We have no reflection. This is, you know, the impact of changing the diameter of the tubing, no impact. And this is heating it up, increasing the pressure of the gas that's trapped in there. Actually, we'll talk more about this. If you heat up a gas like this that has a liquid that can go ahead and go from its liquid to its gaseous state, two things. One is you're giving the gas particles that are already gas particles more kinetic energy, so more pressure. The other thing is it's heating it up, you're going to have more amount that can actually, you'll have a more amount of saturation. So, have you ever heard that warm air can hold more water vapor than cold air? It's kind of true. Warm air can hold more. It's not that the air holds it, but the equilibrium vapor pressure is higher. So,
Back in Wisconsin, we used to say it gets too cold to snow.
yeah, I've heard that too. That's why you're like, it can't snow, it's too dang cold. But, okay, a couple videos. Kevin's gonna hate that he missed video day. We call volatility somebody that's kind of quick to go off if they're volatile. And then so similarly, we say a substance is volatile if it kind of relatively easily transitions from its liquid to its gas state. Again, it doesn't mean that it is it's boiling. It just means that it has a high equilibrium vapor pressure. So in general, the more volatile, if something is volatile, then it's easier to go in its gas phase. I'm going to throw this at you because we've been talking about intermolecular forces, intermolecular bonds, intermolecular forces. So if something is relatively easy to something volatile, it goes from its liquid to its gas state. What would you say about its bonds, intermolecular bonds? They're really weak, yeah. So here's where I draw a few beakers on the next few slides. So I'll call this guy A, and he is going to be volatile, and then this guy is going to be non-volatile. When comparing two liquids at the same temperature, so I'm going to say T is equal to 25 degrees Celsius for both. I'm going to go ahead and put these, I'm going to cap them. How would I draw dots? If I were going to draw dots and they're in equilibrium, would I draw not very many or a lot of dots here? A lot of dots. Yes, because it's volatile. Exactly. There's many things in science, chemistry included, that I just kind of think through, and I'm like, oh, well, that's how that goes. Because you told me if something's volatile, it has low intermolecular bonds, or strength or whatever. And so, yeah. So what would you say with regard to the equilibrium vapor pressure of this volatile guy? Is it high or low? High. Yep. If I were to put a pressure gauge, sometimes I put a little pressure gauge here. If we put a pressure gauge here, this would have a high EVP, equilibrium vapor pressure. Yep, you got it. In italics, the more volatile liquid will have a higher equilibrium vapor pressure. When in doubt, draw beakers. Little white glass over them, let your system come to equilibrium. Okay, so let's look at another scenario. Again, A and B. We'll make the A more volatile and the B less volatile. I'm going to put watch glasses over them. There's liquid down here. Okay, now this one's a little bit different. We'll put gas particles. Notice that I'm going to let them come to the same equilibrium vapor pressure. So I'm going to make this one volatile and the other one's non-volatile. So here's my watch glasses. So here are my particles. I didn't count them, but hopefully they're very similar. So if I put a gauge on either one, I'm going to have very similar. So I'll put EVP, equilibrium vapor pressures. I'll put same. Now, how could you do that? Well, the catch is if you say, how How could we do this with regard to temperature? Would we jack up the temperature or lower the temperature of this first one? Lower. Yep. If we tap it down, make it feel more chill, maybe make this a little warmer. Yep. So this would be a lower temperature. Lower T, higher T.
This is the formula for this here. Temperature, pressure.
No, no, because this is different. The PV equals nRT goes to one substance, and we're kind of comparing, and kind of at the crux of all this is volatility, and volatility is regulated with intermolecular bonds. So, yeah, it's different. But we will be using PV equals nRT momentarily. Bring my handouts. Yes. No, maybe. Oh man. Okay, so these are curves, different substances from left to right. And let's see, how do I do this? These actually, the way you think of them, is think of this as something in its liquid state, and this is something in its gaseous state. Liquid, gas, liquid, gas. So kind of that transition line is what we call the equilibrium vapor pressure at a particular temperature. So this first one, ethyl ether, and by the way, you're like, I don't know what ethyl ether is. Well, we'll be talking more about kind of, when we talk about ethers, what sort of what we call functional group, what can you expect from an ethyl ether. But let's see, let's pick on 20 degrees Celsius. At 20 degrees Celsius, its equilibrium vapor pressure looks like, oh my goodness, I'm guessing, what do you think, maybe 60? That's how you do that. 20 degrees Celsius, where it intersects, and that is the EVP, equilibrium vapor pressure, at 20 degrees Celsius. Ethyl alcohol, maybe 20 degrees. It's the yellow one. Oh, yeah, we can do that. So for the yellow one, let's pick on 20 degrees Celsius. Let's go up. Okay, is its equilibrium vapor pressure greater or less than ethyl ether? It's less. Lower equilibrium vapor pressure, less volatile. Does that look right to you? Yeah. Water. Now, water's an awesome thing. Remember, it's got those hydrogen bonds going on. 20 degrees, it would be really hard to pick off, but I'm kind of thinking it's even less. Okay. Let's find water, so that purple one. Go to 100 degrees. Okay, 100 degrees. Now, the interesting thing about water at 100 degrees is that's the temperature water boils at. Let's see what the equilibrium vapor pressure is of water, that purple line, at 100 degrees Celsius. I got here, here, right? Over here. This is kilopascals. So I know you guys told me atmospheric pressure is 1 atmosphere, but this is going to be atmospheric pressure in the units of kilopascals. Because a long time ago, just the other day, we said that the temperature at which something boils is when its equilibrium vapor pressure is equal to atmospheric pressure. Remember we said that? All right. Last but not least, we have ethylene glycol. And again, we'll be talking more about what would that look like. But what do you think? Ethylene glycol is probably the least volatile? I'm thinking so. So here's isolating water, and the units aren't kilopascals over here. Now the units are millimeters of mercury. 760 millimeters of mercury. I know what you'd say. See, this is why they need a better editor. This would be in millimeters mercury. I know that because 760 millimeters mercury is 1 atmosphere. So here we are at 100 degrees Celsius, and the equilibrium vapor pressure is 760. Now, one of the things I don't like about this is you saw it a minute ago, actually the equilibrium vapor pressure for water goes on up. It doesn't abruptly stop at 100. So don't be freaked out about that. Speaking of equilibrium vapor pressures for water, This is a table from your textbook, and I actually made copies. Oh, I know. It's over here. Just losing it. I don't know why. I just thought. The problem we're working actually will kind of look. This equal vapor pressure of water. So hopefully we kind of see as we increase the temperature what happens to equilibrium vapor pressure. It increases, yep. So for instance, like we were running, let's see, now it's Fahrenheit, oh, this is Celsius. I'd have to do a little conversion. Of course, 0 Celsius is 32 degrees Fahrenheit. Okay. So even negative 10 Celsius, oh no, I think we got even colder than that. But can you see where the equilibrium vapor pressure of water is 1.95? The air is so dry. That's why when our furnaces run and they suck in that cold air, it is just dry as a bone, and our houses become dry. Okay. In the summertime, we're probably up here-ish, I don't know, 27, 28, 29 degrees Celsius. And notice that the equilibrium vapor pressure of water is a lot higher. Put another way, if we're at 100% what we call relative humidity, we've got, in the warm case, we've got 25 or to 28 torrs of pressure, and here at 100% RH, we have 1.95. Come back. Anyway, so, but you guys got that. This is just another table, and I didn't take the time to look why it's that much different, but maybe it goes up, but this one goes to 110, and this one goes to 100. This one's in units. Oh, this is in units of 2, okay, and this is in units of 1. That's right. Just in case you need it. Yeah, you may find out. So we'll take a look at this problem. I have 2 problems. So I'm going to draw this problem here in a minute, because it definitely is a drawing sort of problem. But what you're going to see on my drawing is basically I'm going to take an Erlenmeyer flask. In the bottom of the flask, I'm going to put that mass of water, 0.110 grams. I'm going to put a stopper on my flask. I know the volume of my Erlenmeyer flask. And the question here is, under these conditions, verify, which means it will, verify that that 0.110 gram of liquid water will all evaporate. And when it evaporates, what will be the pressure of the water? Assuming ideal gas law behavior, or ideal gas behavior. So we're going to use the ideal gas law equation. So we're working these 2 problems, and any problem like this, we can kind of kick it out one of 2 ways. So, for instance, we could calculate if that entire mass, we could calculate, given that volume and that temperature, we could come up with, we use P equals nRT, and come up with N, and say, well, I know how much water vapor could be held at that sort of thing. Okay, we can use this and say, I know pressure, I know volume, I know temperature. How many moles of water vapor could I hold in that Erlenmeyer flask? We could do that. That's one way. And then compare what if that number was larger than our 0.110, then be like, dude, you got plenty of room to evaporate that. Okay. If it was smaller, we know it wouldn't all evaporate. Or we could go ahead and assume that that 0.110 grams is going to go all evaporate. In fact, it said verify that all the liquid water will evaporate. Actually, the second route's what we're going to do. And in that case, we could use P equals nRT to calculate what the partial pressure would be. to make sure it would all evaporate, the last thing that we're going to have to do is to, once we come up with the pressure of water vapor, make sure that it's under the equilibrium vapor pressure at that temperature for water. So that's what we're going to do. So the second one actually makes more sense. So here's my diagram. It looks like this. Do, 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 do. Not a beaker, it's an Erlenmeyer. Here's my stopper, make it a closed system. Here's my puddle of water. That is my 0.110 grams of H2O liquid. And the volume was given is 5.35 liters. The temperature was given 25 degrees Celsius. Here in a minute, I'm going to actually show you how we're going to have to go to Kelvin by adding 273 units. Okay. Just for kicks, I'm going to take that chart I gave you, look up 25, and notice it's not all in twos, is it? It kind of goes twos and then it slows down. I don't know. It's threes over here. This is a weird, another weird. It's 10. Anyway. So when temperature is equal to 25 degrees Celsius, the equilibrium vapor pressure or vapor pressure of H2O gas is 23.8, and then units are torrs. Okay, so I'm going to compare my pressure to make sure it's under that to know that it wouldn't be saturated. So here we go. I guess I didn't need to draw that. So like I said, we're going to go with the second one. We're going to calculate the pressure that would be in the bottle, in the Erlenmeyer flask, if all of that water evaporated. So we're going to have to do our PV equals nRT, rearrange it, and we're solving for pressure. So we'll divide both sides by R. You know, the hardest thing, I think, of working isogassol problems is getting this first part right. It's like anyway, it's algebra. So we're going to have to, we can come up with N from using that 0.110, and I'm not going to show you, do you guys know what the mole amount of water is? 18.02 grams per mole. Okay, so you guys probably have to show this mole mass of water calculation, but we're going to do the 0.110 grams of water as our puddle, molar mass of water, 1 mole per 18.02 grams, and that 3 sig figs, that gives us 0.00610 moles of water. So that's our N value. We're on our way to plug and play. And so then, what else we need? Let's see, we got that one. The T, I figured we need to fix our temperature. So we have 25 degrees Celsius, and it's to the nearest 1, so we don't have to worry about the 23.15. So 273.15. So we just go plus 273 units. That gives us a 298 Kelvin. Our volume was 5.35 liters. And the value of R we're going to use is 0.082058 liters atmospheres per mole Kelvin. So plugging in the numerator, we have that 0.00610 moles times 0.082058 liters atmospheres per mole Kelvin, that's R, times our temperature, which is 298 Kelvin, and divided by V, which is 5.35 liters. And then, as is always the fun part of working problems in physical science, we get to cancel units. Moles cancel, Kelvin cancel, and I get liters cancel. And we're left with units of atmospheres, which is perfect. Well, sort of, because here in a minute we're going to have to compare it to torr somehow. We can do that. Oh, sorry. So how many sig figs? 3. I'm liking 3. So 0.0279 atmospheres. It's funny because I get so excited my units come out. I don't care about the number, I just care about my units. 0.0279 ounces. Cool. So like I said, in order to verify that that mass of water will evaporate, we still have to compare that to our equilibrium vapor pressure. So from the table, we picked up, oh, I see what we're doing here. It's like, what? So instead of converting the torr to atmospheres, we're actually converting the atmospheres into torr. So here we go. The pressure we came up with is 0.0279 atmospheres. We're going to go to torrs through millimeters of mercury. So that we know that 1 atmosphere is exactly equal to 760 millimeters of mercury. So now atmospheres cancel. Does anybody remember the relationship between millimeters of mercury and torr? They're equal. Yep. So then, oh, I guess I'm not. All right, so I'll go ahead and resolve this. We have 3 sig figs in the first term. Notice that this is an exact relationship, the 760 over 1. So I'm allowed 3 sig figs. So 21.2 millimeters of mercury. I wonder if I just automatically, I don't know what my notes do now. Let's see what I do next. Well, anyway, is that what this one says? Yeah, 23.8. Yeah, it's a little sloppy, Mrs. Snipes, because this unit is torr, and so actually I went right to the millimeters of mercury. Sorry, guys. I should just put one more term in there. So now if we compare these two numbers, do you see where we're under saturation? It will all evaporate. We did not bump up against the equilibrium pressure at that temperature. So we're done. Since the pressure exerted by the water vapor pressure is less than the equilibrium pressure at that temperature, all of the water will indeed evaporate. We have verified. Another problem. It's all about the problems. I'll just write the picture here. Okay, here we go. I know you're like, oh, story problems. Ah, the bane of my existence. I know in high school or in grade school, everybody hates story problems. But let's draw a picture. Okay, I'm going to go ahead and use an Erlenmeyer flask again, if that's okay. So here's my Erlenmeyer flask. Oh my goodness. That's a crazy looking Erlenmeyer flask. Put a stopper in it. In the bottom, I'm going to go ahead and use liquid water again. Instead of that 0.110, it's going to be a whopping 1.25 grams of H2O liquid. The volume is bigger though. The volume it will hold is 9.70 liters. The temperature is a little warmer. 40, remember I've got a decimal there, so 40 degrees Celsius, I can add 273 to get that in Kelvin if I need to. So the question is, verify under these conditions that, again, verify that not all of the water will evaporate. So in other words, when this reaches equilibrium, which I'm kind of drawing it into the experiment now, I'm actually going to have a little puddle left. Okay, we're supposed to verify that. Verify under these conditions not all the water evaporate. Determine the partial pressure of the water vapor. Determine the partial pressure of the water vapor is in the flask and calculate the mass of water that did not evaporate. First off, I can tell you the equilibrium. I can tell you the partial pressure of the water. All I gotta do is take this here thing, find 40, and I can tell you if there's some residue left, that's going to be the partial pressure of my water. 55.3 millimeters of mercury per torr. That is easy. calculate the mass of the water, calculate your puddle that was left. So again, we can kind of look at these two approaches. And I bet we're going to go with the approach that we didn't use before. All right. So we can calculate, given the volume and the temperature, we can PV is equal to nRT. Given the volume and the temperature, okay, we can assume that it will all evaporate and use this as the equilibrium vapor pressure at 40 degrees Celsius. Notice that says 35. Is it just me? It says 35 instead of 40.
Yeah.
Okay. Like, what? Now that's not OpenStack's problem. Okay, we can do that. And then what we'll do is, if those number of moles, we'll convert that to grams, and if those grams are less than these grams, okay, then that means this isn't all going to evaporate. And actually, that's the route we're going to go with, because we know there's going to be a puddle left over, and that will get us down the road to how much didn't evaporate. Alternatively, we can do what we did before with this sort of approach. We can calculate the mass of the water that would be present in the equilibrium vapor pressure if it all did evaporate. And that doesn't make sense because we know it's going to all evaporate. That won't get us down the road. Oh, I think I got one. We're going to do this one, I think. We are going to do this one. Calculate the mass that would be in there. Anyway, let's just work it. Yeah. Second one's the best. The first one is the first one last time? Oh, drat. Okay, so here we go. We are going to come up with a number of moles that would be in at this temperature and this volume if it was at equilibrium. I'm curious to see what temperature I use. So if we're going for n, the number of moles, we rearrange and we get PV divided by RT. PV over RT. So we're going to have to convert the pressure to atmospheres. See, I'm back to 40. So back to 40. And it was, the sheet I gave you says in terms of torrs, which is equal to millimeters of mercury, you're looking at 55.3. I need to convert that to atmospheres to use the R that I've been using. So it looks like this. If 55.3 millimeters of mercury is my first term, I take that times 1 atmosphere over 760 millimeters of mercury. Units of millimeters of mercury cancel. I have units of atmospheres. How many sig figs? 132. So my pressure to plug in is 0.0728 atmospheres. So that's pressure. I know volume. I know R. Now, so temperature, I got to fix my 40. So to fix my temperature of 40, I add 273 units. That gives me up to 313 Kelvin. So now I'm ready to plug in. Goodness gracious. So N will be equal to, in the numerator, we have the pressure pressure 0.0728 atmospheres. In the numerator, we have the volume, 0.970 liters. In the denominator, we have R, 0.082058 liters atmospheres per mole Kelvin. And then also in the denominator, we have that temperature of 313 Kelvin. And N should be moles, right? So let's see, atmospheres cancel, liters cancel, Kelvins cancel. We have units of, that's that funky, the inverse of moles in the denominator is equal to units of moles. So how many sig figs? 3. Yep. So I got 0.0275 moles of H2O. 0.0275 moles. So we're almost done. Now all we got to do is find out what is the mass of that and compare it to our 1.25 grams. Of course, we'll use the molar mass, so here we go. If we take those moles, 0.0275 moles H2 over 1, times the molar mass of water, which is 18.02 grams of H2, or 18.02 grams over 1 mole. Moles will cancel, we have grams. 3 sig figs again. Drum roll, please. 0.495 grams of H2O. So that's what you have floating around there at equilibrium. 0.495 grams of H2O. So how are we going to find the mass of the puddle? Subtract. Yep, take this, minus this. Exactly. So we don't do as much subtraction as in chemistry as we do multiplication division. Notice that I have my 1.25 grams minus 0.495 grams, and I have 2 decimals in the first term, 3 decimals in the second, so I'm only allowed 2 decimals in my answer. That's why it's 0.75 grams. I know, yeah. She asked, do I need to put the H2 on there? It's optional. If we had different masses, you definitely would have to. Masses of different things. So in bold, did you notice that the air in the flask had no effect on the system or our calculations? It's kind of cool. It's behaving independently. Equilibrium vapor pressures don't care what else you got going on in there. Dun, dun, dun. I can't remember how many pages this was. Man, there were some of them. I'm just like, oh, just slogging through the problems over winter break.
I was just going to ask real quick, but for the calculations all up to that last part were the volume of the flask, not the volume of the water in the flask.
Right, volume of the flask, because we're worried about the gas, and the gas is going to fill the volume of the Erlenmeyer flask. Yep, yep. Very good. Well, that's all I got. Kept you all. I didn't keep you over though. I was like, oh man.